let xn be an i.i.d. sequence of random variables. That sentence is the opening salvo of a healthy fraction of theorems in probability theory. So we'd better understand just what it means. A sequence xn of random variables, that is, measurable maps from a common probability space to a common measurable space, is called i.i.d., or independent and identically distributed, if all of the random variables are independent, and if they all have the same law. The law of xn is the same as the law of, say, x1 for every n. Remember that the law, or probability distribution, is the push forward of the probability measure to the state space S. We will most commonly be interested in such sequences in the case where the state space is a Euclidean space equipped with its usual Borel sigma field. But this makes sense in general. It makes sense provided such things even exist. It is not a priori clear that they do. In general, we would like to generate countably infinite sequences of random variables that have any prescribed laws that we want, not necessarily all the same. Constructing finite sequences that have this property is fairly easy. Let mu1 through mu(n) be any sequence of probability measures on any sequence of state spaces, S1 through Sn, equipped with sigma fields B1 through Bn. We're going to construct a common probability space on which to define a finite sequence, x1 through xn, of random variables, having those measures, mu1 through mu(n), as their laws. And we'll do it simply using product measure. We'll let our sample space be the product of the state spaces. Our sigma field will be the product sigma field. And our probability measure will be the product measure of those finitely many measures on the different state spaces. Then we will define our putative random variables on the sample space omega, taking values in the different state spaces Sn, in the most simple and natural way that we can. Xn is just going to be the projection map from the product down to the factor Sn. That is, pi n of x, which is of the form x1 through xn, is just the little nth component of that vector. Those are, of course, measurable maps with respect to the product sigma field. In fact, we have a theorem that says that the sigma field they generate is the full product sigma field. Those random variables are independent and have the prescribed laws. And that is just an easy calculation. Let's check. The probability, that is the product measure on the sample space that we've defined, of the set where x1 is in B1, x2 is in B2, and xn is in Bn. For any choices b little n in scripty b little n, is the product measure of the set of all vector x's in the product space for which x1 is in B1 all the way through xn is in Bn. In other words, it's just the product measure of the product of the sets B1 through Bn. And by the fundamental property of product measures, the rectangular law, this is the product, mu1 of B1 through mu(n) of Bn. Now apply this with Bj equal to the whole space Sj for all j not equal to n, and what we get is that the probability that xn is in Bn and x1 is in S1, which is automatic, and x2 is in S2, which is automatic, and so forth, is equal to mu1 of S1, mu n of Bn, mu capital N of S capital N. But of course, these are all probability measures, and so all of these terms are just 1, and so we get mu n of Bn. And so in one fell swoop, that shows that the law of xn is mu n, and the random variables xn are independent. Let's look at an example. Suppose we want to construct a finite number d of i.i.d. standard normal random variables. Remember that the standard normal law, which I'm calling mu here, has this Gaussian density with respect to Lebesgue measure on the real line equipped with the Borel sigma field. So following the construct of the last lemma, we need to take as our sample space the d-fold product of the real line equipped with the d-fold sigma field product of the Borel sigma field, which is exactly the Borel sigma field over the reals product d times, and equip that with the product measure of this measure mu. Then the projection maps, which are right here, are i.i.d. standard normal random variables. Now we can go one step further here and look at the joint density of those random variables because they have one. Indeed, as you'll show on your homework, if you have a bunch of laws with densities, then their product has a density with respect to the product measure. Now the product measure here will be the d-fold product of the Lebesgue measure, which is the Lebesgue measure on Rd. And that density is just given as the d-fold tensor product of the density on each factor. So we can compute that. This is a function of d variables, which is just 1 over root 2 pi e to the minus x1 squared over 2 times 1 over root 2 pi e to the minus x2 squared over 2 times e to the minus xd squared over 2 times the appropriate factor. Now we can combine that, putting the 1 over root 2 pi's together, and putting the exponentials together using the basic property of exponentials. This is minus 1/2 the sum, j going from 1 up to d, of xj squared. In other words, it's e to the minus 1/2 the Euclidean length of the vector x squared. This is what we call the standard normal density in d dimensions, which I'll write like this. And we'll explain that notation a little bit later. This refers to the d by d identity matrix. Following a mold like this, we can easily construct any finite number of random variables taking any putative laws that we want. But what about an infinite sequence? Well, if we'd like to follow the same outline, we need to be able to define infinite product measure. And that's what we're going to do in the rest of this lecture and the next one, following a mold called Kolmogorov's extension theorem. Here's the idea. In the last example, where we had a bunch of measures on the real line that we'd like to take the product of, we take as our sample space the product of the real line as many times as we need. So we're going to do that here too. We'd like to take an infinite sequence of measures and define a sample space on which we'll have random variables that have those infinitely many laws as their laws. So that sample space is going to be r to the infinity. R to the infinity here more properly denoted as r to the n natural numbers. That is, the space of all functions from the natural numbers into the real line, or as we usually refer to them, sequences. All sequences, xn, in the real line. Now we can think of this as a kind of limit as d goes to infinity of rd, where rd here we will view as being inside the sequence space by the usual inclusion. x1 through xd get considered to be the sequence x1 through xd just followed by zeros. With that sequence of inclusions, we get that r1 is contained in r2, is contained in r3, etc., and are all contained in Rn. We're going to take advantage of this sequence of inclusions, and we're going to use it to define a topology on this sequence space. Now, to make things a little bit easier, and to rely on compactness results from the real line, we are going to restrict our sequences initially, not to r to the n, but to the unit interval to the n. These sequences will all have terms between 0 and 1. And we're going to call that space Q, the infinite cube. We have the same sequence of inclusions, this time from the unit interval to the d into the unit interval to the n. And we're going to define the topology on this infinite cube according to those inclusions as the topology of pointwise convergence. That is to say, suppose that we have a sequence in Q, x superscript 1, x superscript 2, x superscript k, etc. What that means is that x1 is a sequence, x1n, for n going from 1 up to infinity, and x2 is a different sequence, and so on. And we'd like to say what it means for that sequence of sequences to converge to a sequence in the cube. And we'll say that that happens if it happens component-wise, which is the same notion of convergence that we have in RD. The sequence x superscript k converges to x if and only if xkn converges to xn for all components n. That is, convergence of this infinite vector is the same as convergence of each of its components. In the finite dimensional setting, we know that that's equivalent to all of the usual metric notions of convergence that we like. In this infinite dimensional setting, it is not. This is our definition of convergence for our current purposes, and this defines the topology on this infinite cube Q. One reason that we're choosing this sort of naive topology is that it allows us to import compactness results from the finite dimensional setting quickly into the infinite dimensional setting. And so we have Tychonoff's theorem, which tells us in this context that this infinite cube is compact. Since we're defining the topology by convergence, it makes sense to state that compactness result in terms of sequential compactness. So the statement here is that if I have a sequence of sequences in the infinite cube, any such sequence has a convergent subsequence. Let's prove that. This is the sort of result that you probably saw variations of in your undergraduate analysis class. But let's just remind ourselves how to prove it using the usual Cantor diagonal type argument. So let's start with the first term. xm1, the first component of each of the sequences xm, has a convergent subsequence. Why? Because these are all in the unit interval, which is a compact subset of the real line. So let's call that convergent subsequence xm1 of k. So that is, as k goes to infinity, this sequence of indices m1 of k going off to infinity, x1 m1 of k converges to some x1 in the unit interval. Now we'll choose a sub-subsequence of that for the second component. So x2 m1k, which is a sequence in the compact unit interval, has a convergent subsequence, which we'll call x2 m2k. And that converges as k goes to infinity to some x2 in the unit interval. And so following this routine, we will construct a sequence of sub-sub-sub-sequences, xj, mj of k, that converge to some xj in the unit interval. And each set of indices, mj, is a subset of the previous set of indices, mj minus 1. And so what that means is that xj of mi of k converges to xj for all I bigger than or equal to j. Okay, so if we could stop this process at some finite point, then at that finite point we've discovered a sub-sub-sub-sequence that is convergent for all of the previous ones as well, and so we've done our job. And this is exactly how one proves that closed bounded subsets of the real line are compact. But we can't stop at some finite point here. We need to have a subsequence that will work for all infinitely many. How do we do that? We just take the diagonal sequence. That is, take xk of mk of k. By construction, and by what we've written here, that is a sequence which is a subsequence of all of the subsequences. And that, for each k, is going to converge to xk. That follows by an epsilon over 2 type argument, comparing for each fixed k as we vary k. and I'll leave the details to you. So we have for each component, this subsequence converges component-wise to some element of the unit interval, and that is exactly what it means for this subsequence of the original x to converge in the infinite cube. So that proves the sequential compactness of the infinite cube with respect to the topology of pointwise convergence. One quick consequence of that compactness result is the finite intersection property. Suppose that we have a sequence of closed subsets of the infinite cube. Now, as usual in any nice topological space, closed subsets of a compact set are compact, and since this is compact, that means these are all compact. If those closed subsets have this property here, the intersection of any finite number of them is non-empty, then the intersection of all of them is non-empty. This is another characterization of what compactness means. This fails for closed sets in the real line, for example. You could take the interval from n up to infinity. That closed interval has the property that the intersection of any finite number of them is the closed interval from the largest index up to infinity, is another non-empty interval. But the intersection of all of them is empty. In non-compact spaces, you can have mass escaping to infinity. But in a compact space, that can't happen, and that characterizes compactness, at least in nice spaces. And here's the proof. Let xm be some element of the intersection of the first m ki's. Our assumption is that that finite intersection does possess some point xm. By Tychonoff's theorem, there exists a convergent subsequence xmk that converges to some point x in the infinite cube. Now notice that xmk, by construction, is in the intersection of the first mk compact spaces ki. And therefore, as we continue to take further intersections, xml will also be in that intersection for all l bigger than or equal to k. Well, ki is closed, and therefore x, which is the limit as l goes to infinity of xml, will be in ki for all I bigger than or equal to k. But that's true for every k, and so therefore x is in the intersection of all of them. So there are some basic properties of the infinite cube equipped with the topology of pointwise convergence. Now we're going to use those properties to prove the Kolmogorov extension theorem. Suppose that on each finite dimensional cube equipped with its Borel sigma field, I have a probability measure, nu n, and suppose that that sequence of probability measures on larger and larger included spaces satisfies the following consistency condition. If I take the n plus 1th probability measure, which is on the n plus 1 dimensional cube, and I restrict it to the n-dimensional cube inside there, following the inclusions that we've been using, what I recover is just the nth probability measure in the sequence. This kind of consistency is critical in order to construct a limit of these nu n's. Kolmogorov's theorem is that if this consistency condition is met, then there does exist a unique probability measure on the infinite cube equipped with its Borel sigma field. It's a topological space, so this is, as usual, the Borel sigma field generated by all open or all closed sets, with the property that that infinite dimensional probability measure, when restricted to any finite dimensional cube sitting inside via the inclusions that we've noted, is the appropriate nu n in the sequence. We will see how to use this theorem in order to construct infinite product measure and therefore construct i.i.d. sequences with any prescribed laws that we want. Right now, it looks like we'll only be able to do that for laws that are defined on the unit interval, but we're going to see also quickly how to generalize this theorem from the unit interval to the real line, simply because the real line can be identified with the open interval from 0 up to 1, which is a Borel subset of the interval from 0 up to 1 closed. And in fact, following Kolmogorov, we'll be able to quickly generalize this to the case where we replace the unit interval in this construction with any Borel set in the real line or in a finite dimensional Euclidean space. Next time, we're going to prove this result and show how to use it.